Here we are looking at rational graphs. We shall look at asymptotes and wholes. And first of all, the definition of a rational function is given by f of x divided by g of x. F of x and gx are polynomials. Here, let's define a vertical asymptote. A vertical asymptote is a line x is equals to a, see the equation of the line, and it's called a vertical asymptote if f of x or y values approach infinity or negative infinity. The graph is approaching negative infinity or positive infinity as x approaches a from the right or a from the left. And this is the meaning. I explained this more over here. I wrote it down here. The other thing we need to remember are the asymptotes, horizontal asymptotes. If the degree of the numerator is greater than the degree of the denominator, then you're not going to have a horizontal asymptote. The other one, if the degree of the numerator equal degree of the denominator, the horizontal asymptote is equal to the ratio of the leading terms. The next one, for the degree, if the degree of the numerator is less than degree of the denominator, then the horizontal asymptote is going to be equal to 0. Y is equals to 0. Here I'm doing some quick review on notation, and I'm going to introduce some notation we haven't used before in class. And here I have a rational function y over x minus 2, and I'm writing here, write the domain of this function. So what's the domain? Remember, when writing the domain, when you have a rational function, I'm thinking of any number which I plug into the denominator will give me 0. And the way I get this number is by taking the denominator, x minus 2, I make it equal to 0, and solve it. I get x is equals to minus 2. And this means if I plug in positive 2 here, I'll be dividing by 0, and 1 over 0 is undefined. So in writing the domain can be any real number except 2. So this is the notation. X, this symbol here, belongs to the set of real number. I'm just saying x is a real number, but x such that x cannot be 2. Or I could write the same thing here, negative infinity to 2, then from 2 to infinity. Or I can say all real numbers except 2. Except 2, maybe here I should say except x is equals to 2. And you can see here, you can see the graph. On this graph here, I have a dashed line which is being approached but not touched. This is a vertical asymptote. And this line is x is equals to 2. And I have another red line. It's not very visible because it's on the y-axis, and its y is equals to 0. That is my horizontal asymptote. And this here is my vertical asymptote. They are being approached but not touched by this graph. And when I'm writing the domain, see, I wrote every x value except any value on the vertical asymptote. And I could do the same for the range. Y is a real number, and y cannot be 0. See, 0 is included. We have an asymptote there. So here I have an example, and I have this function. It's already factored out, and I'm going to start by finding the domain. And in finding the domain, I just need to take each of the denominators, make them equal to 0, and solve. For example, I could do x plus 3 is equals to 0, and I get x is equals to negative 3. Okay, so I know here x is all values, all real numbers, except -3. So x cannot be -3 and x cannot be -2. So that is the domain. Remember, I can use other notations. Okay, the next one, I'm going to find the horizontal asymptotes. And this one I get by comparing the degrees. So if I look at this function, if I take x and x, when I multiply this out, this is going to be x squared, the same at the bottom. So that means the degree on top, the highest degree on top is going to be x squared. On bottom is going to be x squared. Since the degrees are equal, the coefficients of these numbers, which is 1 and 1, is going to be my horizontal asymptote. So y is equals to 1. Then the next thing I'm going to do is to find if there is any hole. And how do I get the hole on the graph? I get the hole on the graph if any of the factor in the numerator and denominator is common. Whatever cancels out. So I have a hole at, then whatever I have cancelled out, I make it equal to 0 and solve it at x is equals to -3. Now the next thing I need to do, I'm going to find the coordinate of the hole. I need to know where the hole is. So I'm going to find the y coordinate by taking the simplified equation which was left, which is x plus 4, and I'm dividing that by x plus 2, and I'm going to plug in the value of x, which I just found here, where the hole is. So -3 plus 4, and then I have -3 plus 2, and that's going to give me 1 divided by -1. So I know the hole is at -3 and -1. So those are the coordinates of the hole. Remember when I simplified this one, let me write it here again, x plus 4 over x plus 2. That's what I was left with. Okay, now the x-intercepts. How do I get the x-intercepts? To get the x-intercepts, I just need to look at my numerator, and whatever was left in the numerator, I make it equal to 0 and solve. So that's going to be x plus 4 equals 0. So that means my x-intercept is going to be at x is equals to -4. Okay, now I look for the vertical asymptote. Now the vertical asymptote, you get it by taking whatever is in the denominator, whatever was left, and make it equal to 0 and solve. So I'm going to write x plus 2. So this is going to be x plus 2 equal to 0. So I solve it. I get x is equals to, I get x is equals to -2. So now my vertical asymptote is that x is equals to -2. Now I'm going to look for all my information on this graph that I made here. So the domain is all real numbers except -3. So where is -3? -3 is where I have a hole. So at that point, the function is not defined. And then at -2, that's where you have this line, an asymptote, a line which is being approached. And then I have these two. This is my domain. These are the discontinuities in the function. The next one is the horizontal asymptote. Y is equals to 1, and you can see an invisible line here. Y is equals to 1, that's why there is a break. And then there is a hole at x is equals to -3, and I got the other coordinate to know the specific location of the hole. The x-intercept is where the graph cuts the x-axis, negative 4. The x asymptote is this invisible line at x is equals to 2. And I also want you to see it meets the definition of what an asymptote is. The limit of p of x as x approaches 3 from the left, as you approach 3 from the left, look at the function. It goes to negative infinity. As you approach 3 from the right, what happens to the function? Coming from this direction, f of x approach, p of x in this case approaches infinity. So here, let's look at this example. We need to find the domain. My first step is to factor it out. So I have x plus 2 over x plus 2 and x minus 2. That means the domain is going to be anything which will make the denominator 0 if I plug in negative 2. So x cannot be negative 2 and x cannot be 2. And I'm getting this by making this equal to 0 and solving. Okay, now I got the domain. I need a horizontal asymptote. I'm going to get that by looking at the dominating terms. In the numerator, I have x, so y, x. In the denominator, I have x and x, so that's going to be x squared. So the higher degree is at the bottom, so horizontal asymptote is y is equal to 0. I need to find the holes. How do I find the holes? I need to check whether any of the factors cancel out. Yes, they do. X plus 2 cancels out. That makes a hole. So the hole is that x is equals to negative 2. Whatever number, whatever I canceled out, make it equal to 0 and solve. Again, negative 2. Then I need to find the y coordinate. And I'm going to do this by taking whatever was left and plugging in the negative 2 there. So it's going to be 1 over, so negative 2. And I'm plugging that into the simplified form. So I get negative 1 over 4. So the whole is at negative 2 and negative 1/4. Okay, so those are the coordinates of the whole. The x-intercepts, how do you get x-intercepts? You need to go to the denominator and see whether there is anything left in the after simplifying. And in my case, there is only 1 in the denominator, so that means there is no intercept, x-intercept, so I'm going to say none. And then this graph is not going to cut the x-axis. Now the vertical asymptote, how do I do that? I need to go to the denominator, whatever is left, make it equal to 0 and solve. So this is going to be x minus 2 equal to 0. So it's going to be x is equals to 2. Now let me analyze what I got here. So I can see this meets the definition of a vertical asymptote because as the function approaches 2 from the left, it's going to negative infinity. As it approaches 2, there should be positive 2, not negative 2. So that's positive 2 because that's what I got right here. Then I get it here to the right, it's going up. So it meets the definition. Okay, so here, this is the function. It's not factored out, so I need to factor it out. And here, I take 4 multiplied by 9, and I get 36. Then I need 2 numbers, which when I multiply, will give me 36. And when I add them, I get 15, and that's 12 and 3. So I use those 2 numbers to split the middle term. So I have 12x and 3x, which is 15. Then I factor by grouping. I factor by grouping, and these are my factors. So I'm going to write them here. So I have 4x plus 3, and the other one is x plus 3. Okay, and for the denominator, this one I already factored out the same way as I did the other one. And the other one is 2x minus 5. And then I'm going to find the domain. So I see the domain cannot be -1, and it also cannot be 2x minus 5. I make it equal to 0. It cannot be x. So cannot be x is equals to 5/2. Cannot be those. Okay, now, so I got my domain. Now I'm going to find the horizontal asymptote. And how do I do that? I compare the degree, top and the bottom, and they are equal. So that means the horizontal asymptote is going to be given by coefficients of the reading terms. So 4/2. So that gives me 2. So y is equals to 2 is my horizontal asymptote. Okay, the other one, I'm going to find in a hole, whether there are holes. Now, is there anything which can cancel out? Anything common? No, nothing common in the numerator and denominator, so I'm going to say none. And then I look for the x-intercepts. X-intercepts, I take the numerator, make them equal to 0, and solve. 4x plus 3 is equals to 0. That means 4x is equals to -3, and x is equals to -3/4. That's the first one. The next one is going to be x plus 1 is equals to 0. X is equals to -1. So I expect to see 2 x-intercepts in the graph. And then the vertical asymptote are going to be given by the denominator. Oh, I made a mistake here. This is supposed to be x plus 3, and x is equal to -3. Those are the intercepts. Now the vertical asymptotes, I look at the denominator this time, these ones here. And I have x plus 1. I solve it, so I get x is equal to -1. That's my first asymptote. And the other one is going to be 2x minus 5 is 0. So I get 2x is equals to 5. So x is equals to 5/2. So those are my asymptotes, vertical asymptotes. So I have 2 of them. Okay, now let me confirm my answers from my graphical representation. So I have here the domain, all the real numbers except these gaps here, -1 and 2.5. And the next one, horizontal asymptote, at y is equals to 2. Look at the head behavior. Don't look at the middle here. The graph is going to be approaching y is equals to 2 for large values of x. The holes, there is no hole because nothing was common. The intercepts, this is the first one, -3, so I got that one. This is the next one, -3/4, so I got that one. Vertical asymptotes are these lines here, invisible lines, as is x is equals to -1, and I have another one, x is equals to 2.5. So those are going to be approached but not touched.